All right, so away we go. I never know exactly when it really kicks in, so I will take a sip of my coffee before we start, so that I know the stream is really going out. Okay, so here we are live streaming again. The topic today is sealed tables, an optimization feature for raptorjit. We started on this yesterday, or well, we did a brain dump on this on the weekend, and pardon me, I don't need that. We did a brain dump on this on the weekend, and then yesterday we had a quick hack at it, and it went surprisingly well. Well, it went well anyway. So we've got a simple example program, which I've got over here, a little Lua program that has a table with a couple of numbers in it, and then we've got a little loop that we want to just-in-time compile, and the loop is pulling those values out of the table and doing arithmetic and updating an accumulator. And what we saw originally, if we would disable loop optimization, because we're interested in the case when loop optimization is not kicking in, because you have to worry about that because it doesn't always kick in. If we take the baseline way that usually compiles, we get this, which is a lot of code. This was all hash table lookups. I mean, we looked at this in depth last time, so I'm just refreshing briefly. This was a lot of hash table lookups to go in to find the math global, find the square root function in the math table, find the t global, x and y in that. And then down here, we were actually doing, floating point math for square root and multiplications and that kind of thing. We did this sealed tables hack in a really crude way. We just said that all table lookups are going to be sealed, which means that at the point we generate machine code, we're going to assume we're going to take the result of the table lookup and inline that as a constant into the machine code. So a sealed table is a table where we have the invariant that we know that the table hasn't been updated since the machine code was generated. And that's the feature that we're implementing, sealed tables. We're going to have a way, we're going to generalize it so that you can flag a table to say this table is sealed. And then if you modify that table, it's going to flush all the machine code, which will then be regenerated. And this will give us the invariant that the machine code is always newer than the contents of the tables. And knowing that, we can do really, really, really hardcore optimizations. We hope, we haven't seen the fatal flaw in IDEA yet, but just context switching back into what we've got to do today. We've got this running, which is nice. One problem is that we did this as a global thing for all tables when really we want to be flagging tables. We probably also want to make this optimization optional, put it in that maybe we'll introduce a new experimental 04 optimization level for optimizations that are still being debugged. And also when we went into the code and implemented this, let me pull that up. It was in this Emacs. We just kind of chucked it in here, right? This is basically the code here. It's only kind of 4 real lines of code, something like. So it's pretty simple at this stage. But we say if one, that really should be checking if this particular table should be sealed. And generally speaking, we just didn't think very deeply about what we were doing, right? We wanted to get something. We wanted to get something that we could test. Oops. My screen is getting off. We want to get something that we could test quickly, and we succeeded in that. But I've got a feeling that when we test this on another example, it's probably going to blow up. For one thing, because this function that we updated, this function for recording indexed loads, this is a recursive function, and so if a table has a meta table, then the table lookup involves several table lookups and function calls and all kinds of things, and we haven't really thought in any deep way about those. What we said is that we want to just generate all the code for all of that stuff, and then, well, we can illustrate that with our little code here. What we want to do is record the table lookup as it would normally be done, which can involve metatable calls, array accesses, anything. We want to just do all of that. Then on this line, we want to just roll back all of that generated code and say, okay, it's great that we did all of that, but this table is sealed. We don't actually care about that. We don't want to do that at runtime. We've done it now at recording time. We don't want to repeat that at runtime. We roll back and throw away all of that code. And then at the bottom, we emit the lookup value as a constant. And in between, we just emit enough guards to make sure that this machine code will only run at the right time, which is when doing a lookup on the same table with the same key. So the compiler is going to we're going to generate specialized machine code that inlines that constant in a safe way. So let's just make a next example and see if it blows up. So our first example is over here. It is this seal1.lua. Let's make seal2.lua. I already had one. Okay, I haven't tested this. Well, hang on. Let's start over. Let's say we're gonna have a table now. Let's start from the other one and we'll just tweak it. So let's just do a meta table. So we're gonna say that this is t index is that, and then t is gonna be an empty table that has a meta table that says if you don't find my key, then look in our index table, which is t index. I mean, so this is kind of in the style of a kind of prototype based object orientation, if you want. So the way it works in Lua is we have a table t. It is this empty table here, but we've given it a meta table that says what to do in certain situations, like if you try to do a lookup on a key. And we're saying that when that happens, when you want to look something up, you should defer to this other table. So it's kind of indirection. So when you do a lookup on this table, it should really forward to a lookup on that table. So let's just see if this crashes or if it optimizes well or if it optimizes poorly. I think that what we hope to see, what we want to see in this case, is exactly the same code as before. So we don't really care how the value was calculated in the strategy that we're taking for this optimization right now. Anyway, we don't care how the value, whether the meta tables were consulted, whether it was really a hash table or an array. We don't care about any of that stuff. We just want to get the value somehow and then specialize the machine code based on that value. So let's see what actually happens. Hop back to our shell. First, yes, we have it built. Here we go on seal2.lua. Doesn't look too bad. Is that the same as we had on seal1? Let's have a look. Yeah. Wow. Okay. Cool. So it looks like the second one worked as well. That's nice. That's always nice when something works. Okay. Let's press our luck and try a third example. And what are we going to do there? So in the third example, our meta table is also going to have a meta table. So let's make this seal3.lua. Now we'll say tfunc will be. We're going to have a meta table that implements lookups using a function instead of a table. So this tfunc is going to be a function that takes a table and a key, and what's it going to do? It's going to give us the same values. It's going to say if the key is x, then return 10,000, else, or just say else, return 10. So this is going to be a special kind of a table. This function is implementing table lookup such that if you ask for the key x, you get 10,000. If you ask for anything else, you get 10. And we're gonna, we'll keep it simple to start with. We will just use this function for doing lookups on our t. So when we do this t.x here, what should happen in principle is we do look up on t. There's no key there. We go to the index meta method to do lookup. It says that we should consult tfunc. Tfunc is a global, incidentally. But anyway, tfunc takes the table and the key, checks the key, whatever. So we hope that it's going to produce the same values in the same way. So again, what we would hope for here is to get the same code that we did the first time. The same code again. This is still the same program, just expressed in a different way. What happens? Let's run seal3.lua. Okay, so that was not the same. Why not? Let's have a look. We got a look up here. Okay, so we need to understand this code, and let's do. Oh wait, hey, we got two traces. Okay, that doesn't matter. Presumably the first one was something uninteresting, but we'll just ignore that. And what we want to do is compare this code here with this code here. So what happened that's different? And mercifully, they seem to both fit on the screen at the same time. But let's just give ourselves a bit of screen space actually. So we'll take this. I'll just align them. That would be quite sufficient. On the left, we have the code that we want. On the right, we have the code that we got. What do we have? That all looks the same. So this is just checking that the globals table is the same, that it hasn't been replaced, which is fine. And then, okay, then what happens? We pull what we have here is this. This is a table that has been referred to directly from the machine code. So there is some table on the heap, and the machine code is referring to that directly by its address in line with the code. And what it's doing here is it's checking that this hash table's mask is 0. So it's a guarded assertion that the hash table with this address is empty, which is interesting. And then what do we have here? We want to say that its meta table is not null, and further that its meta table is this other hash table. Interesting. So what has happened here is let's refer to our source code so we can make sense of it in those terms. So the first hash table that it refers to, that it wants to check is empty, that is presumably this one here. This is where we have an empty. So it wants to check that that hash table is empty and that it has a meta table. So these two lines here are checking that it's empty. These two lines are checking that it has a meta table, and this last line here is checking that its meta table is a specific table, okay, which is going to be this table. So we got pointers to 3 objects inline into the machine code. They're all hash tables. The first one is the globals table called _big G. The second inline pointer is a pointer to this one here, and the last one is a pointer to this one here. So the machine code is specialized on those things. Now, what I said was that we wanted to get the same machine code for this one that we had on the previous one. So this is not what we want. So the question now is, why do we have these extra tests, and can this be related to any of the implementation problems that we were kind of already half conscious that we have? So there's going to be some kind of a recursive lookup going here. I don't really know what the effect of that is likely to be in the code. So could we just, for a first step, just to make our lives a bit simpler, we'll go in and we'll take our special sealing So the sealing optimization, the idea once again is that we want to do the lookup, which can be very, very involved. It can be calling functions, recursing into metatables and metatables of metatables and all that kind of thing. We don't care about any of that. We just want to get the result, and then we want to inline that into the machine code. So if there are any kind of recursive operations, we want to ignore those. We want to have that all play out until it comes up with the actual ultimate value, and then that is what we want to put in. And this makes the sealed tables optimization reasonably aggressive. So the idea here is that we would say that this table is sealed, for example, and then we're gonna capture all of the lookups on that, even if there's no guarantee that a new lookup would have the same result as the last one, right? Like if the meta table is a function, it could be returning a random number, and every single lookup could have a different result. And what we're saying is that if you seal a table, you're going to get the first result. The machine code is specialized for that first result. So if you have a table that has a meta table that always returns random numbers, and you seal that table, then it's your own fault when you keep getting the same value all the time. So anyway, putting that in code terms, I just want to go in again and refactor things very slightly so that we only do this sealing thing once. We don't do it inside a function that's potentially calling itself, because I just don't know how that's going to play out. So it just makes it a little bit harder to think about things. So this is the actual main looking up function. This is the one that we've hacked, and this is the one that recurses and can be called from different contexts. So let's just take the code that we wrote and pull it out a little bit. So what do we have? Oops. The wrong Emacs. So we'll just well, let's go back to the bytecode where this gets called from. So here's the way that it gets called. I think that this one is putting a on the outside. I think it's putting a bound on how much recursion it can do and that kind of thing. So the point is that here we're outside any kind of recursion that might happen. This is the top level of code generation. So actually, maybe after this would be the right place. Maybe what we would want to say is okay, but this is called also from quite a few different places, so it might actually be better to put a new. Okay, for now, let's just do it like this. We'll say if one, just to indicate this is something that we should really be conditionalizing in a good way, then LJ seal. Okay, so tiny bit of copy and pasting, we'll forgive ourselves. So now we're going to do all the lookup recording, and then afterwards we're gonna consider doing the sealing optimization, and to do that we're going to need to know this value that we had before, which is before we do any of the recording for the lookup, what was our latest instruction, so that we can do a rollback, because we're going to record the full elaborate table lookup, including all the meta tables and all the rest of it, and then we're going to roll back the IR code, which just means unemitting a bunch of IR instructions, so that as if that machine code, also that machine code will not be executed at runtime. So every time we pass this, we're going to also need to pass in the rollback address. So let's see if we already have that somewhere. We just scroll up a bit. No, okay. So let's get it. We will just. Yeah, so we need to save it actually before we go in here. I guess we could put it in that record. So the whole point of this IX record is to keep track of state while we are doing our lookups. So actually, it's probably pretty natural to put it in here. If we would just say IRF roll back. Let's say start. How about that? We're going to have this RB start. It's going to be the starting address for the purpose of rollback. It'll be in this struct. We're already passing the struct around everywhere. All we've got to do now is make sure that we initialize it with the right address. So let's see where that IX is being initialized. Where is it declared? There. Okay. Here it is getting initialized by the look of it. Let's say IX dot RB start is Yeah, and an IR reference is just the number of an IR instruction. So I can flip back and illustrate that. These are IR references, these numbers. So what it's saying is if when we start recording the code, if we were here, for example, or if this was the latest instruction that had already been compiled when we started doing lookup, then we would remember this 3 as the IR ref, and then we would generate all this code. And then when we do our rollback, we just delete, drop all of those instructions until we get back to there. So that's the point here, is just to remember this. Where was the IR up to before we started doing our lookup compilation. And I think there's somewhere else that we create one of these structs that also needs to be initialized. Let's just check the other uses. It's called record. Oh, sorry, what was it called? It's called a record index. Record index. Okay, there's one. And we're going to need to be a little careful because when we're rolling back code, this, maybe we'll come back to this one later. I think this is when we do, we're going to come back to that one a little bit later. Let's just check if there's any other uses. You know, Lua, here's, it's already got a record index. Yeah, right. So I mean, we just need to be a little bit careful with other cases. So Lua as a language has a lot of things like operator overloading and all that kind of thing, and it means that you can end up doing table lookups and meta method lookups and stuff in a lot of different places. You might say A plus B, and it might end up being a call to the add meta method and that kind of thing. So we're going to have to be really careful that we do this consistently for everywhere a table lookup is done, which is not just going to be on a syntactic table lookup, but also in a lot of other situations. And since we're doing this machine code, this generated code rollback thing, we're going to need to make sure that we roll back the right instructions and don't go with too much on that kind of thing. So I think we're just going to take this one case at a time for now, because we already have a failing test, so to speak, that we had over here. We have this code that we don't want. So what we're going to just try to do now is get that compiling the way that we want, and then we'll take the next baby step. So back to it. In this main bytecode recording function, which is huge, LJ record instruction, now we are initializing the rollback point to be before we did anything here, before we started before we started recording our lookup. And then come down here, we have this function that we haven't written yet that is going to need to know, okay, we're already passing in this record index, so now it has all the state that it needs in there, presumably. So now what we do is we're going to write this function LJ-seal-index, and that's going to be the new home for our optimization. And then we'll look again at the generated code and see, now that we've got a little bit less, a smaller kind of mistake surface after this, once we know it's not getting called recursively, it'll be a little bit easier to think about, I think. So we go back up and find LJ record IDX, and we'll make the new function. And it's going to have the same return value. There should be some kind of an IR reference. Act IR reference. Then we call LJ-seal-IDX. And we're going to just snip out the code that we already had, like that, and put that here. We already have the conditional somewhere else, so all we need to do is make sure we have access to all of those values. So okay, so RB start is now in the record index. And this old v that we are referring to is that. So that has a slightly non-trivial value. So why, I mean, so the value we have in our subroutine is this record index old v, but that's not always the one that we had in the other function. So it's checking if a kk pointer is a constant pointer to a constant. So is this an immutable pointer to something that is also immutable? If so, I'm not quite sure what the meaning of this line is. We're going to have to come back to that. We're going to use this old v here for now, and we're just going to make a note. Old v is not necessarily the same as old v in board. So that is something we're going to come back to. Meanwhile, is this anything that could conceivably compile? Do a rollback all the way back to before the lookup started. Great. Roll back all our instructions to avoid runtime lookup. Sure that we're looking in the right table. Only referencing variables that do exist. Sure that we're looking at the right key. Inline the result. That has at least a 50-50 chance of compiling, I reckon. Let's have a look. Res. Here we don't have anything called res. Why don't we just say this in that case? Okay, that compiled. And again, we're doing this on the raptorjit code base just because it was convenient. This is really intended for raptorjit, but it doesn't make a big difference for our purposes actually. Let's run it again. Wow, crazy things happen. Okay, now we've got a lot of different traces getting compiled. Which is a bit interesting. So look at the first two. You have something on seal.lua line, seal3.lua line 8. Let's plot the code. Here we have a trace that starts here, and it tests the identity of all of these tables. No, it's 3 times that looks I think it looks kind of deeply broken in the sense that this is an IR instruction that's referencing an instruction that comes after, which is nonsensical. So I think we've totally trashed the IR code, which is kind of fun. I haven't done that before. That's a personal milestone. So I mean, the IR code is just an array of bits and bytes, and it seems like we did something not so good. Okay, so let's have a look at what we might have done to mess that up. Specifically, that we ended up with these. I don't think that we want. Is that? It's probably checking the identity of the globals table. The only thing is that it's referencing. It's referencing one operand. So this is checking the equality of a table. So this is probably the table equality guard that we emit. It's probably this. and the constant argument. So one of the operands on this equality guard is a constant appointed to an object on the heap, and that should reasonably be this because we have a table that we have specifically interned into the constant pool of this machine code, and that is fine. But then presumably, then the problem is this here, where we want to compare that with the runtime value of the table, and the runtime value of the table then is something we've already rolled back, presumably. Oof. So that makes things a little more tricky, right? So if in our guard we need to refer to a value that was computed during the lookup, but we roll everything back so that we don't have that value. But you know what? Is this the right field to look at? So what I think is happening here is that while we're doing our lookup, we do a bit of work. We go off this meta table and everything, and the intention of this guard is to check that the table we're doing the original outermost lookup in is the same. The runtime value of that outermost table is the same as the one that we saw at compile time, and I don't think that should have to be computed. I mean, this the value of that table should already be a kind of an input here. It should be at the top level. So I think this might be the wrong value. Maybe during the lookup we're setting this ix tab to something which is not the value that we actually want here. So we need to have another look at the definition of the struct, see if that's the right field, and if not, if there's another field, and if not, then whether we should introduce another field. So let's see what is ix tab, if not the kind of original outermost table. Okay, it seems a little ambiguous to me. I mean, is this something that gets updated as we recurse, or is it something that's initialized once? So let's have a look at how it actually is done. Record IDX. Okay, ix tab equals. Okay, we can see immediately anyway that this is getting updated with other values. So if we want to have, I mean, I would like to know what is the original, what is the outermost table that we're doing the lookup in. That's the one we want to check on. I don't immediately see that we have that remembered, so we're going to add that. We already added this rb start, and now we're also going to add tref to the which is the original table index object. When we read the diff before we commit this, we can think about whether that makes sense, if this line of code survives. Okay, so we want where do we initialize this? There's quite a few places where that is set. Let's just narrow ourselves to this particular function of interest. Okay, so it's not really happening in here. It must be in in one of these subroutines we have like forward mm lookup. Okay. Okay. Let's just add this. No, we can't do it. But what we want to do is when we update this table, we want to not, as we recurse for updating the table, what we want to do on this original table is to just keep the first value and not be changing them. So let's see again all the places that we do this update on the table. There's one place that we do it. Is that okay? That would need to be updated. Okay, so what about if we just do it for the simplest case, because I don't really know if this is the right approach to be taking, so let's just find the case that corresponds to what we're actually doing. Okay, that's a meta table lookup, so it's a little bit hard to identify. So okay, let me take that back and let's say this. This is pretty rough, and now beautiful tiny little patch is now getting a little bigger. But we'll live with that. Well, I don't have a terribly good feeling about this. Let's just persevere anyway for the moment. I mean, this is turning into quite a big patch, so probably what we would really like to do is maybe grab, if that old v that we had in the function before was really the right one, we probably want to just fill it in there instead rather. But anyway, let's see what happens here. And then we're going to make sure we initialize this rig tab. Yeah, initialize that to 0. I think also that whether that's correct. Well, so we really need to. I guess we managed to pick some low-hanging fruit for the simple example, but now we're gradually being forced to actually understand the code. So we'll indulge in a little bit of hack and slash now, as just as a kind of a learning experience, and then we'll need to probably come back and stare at this a little bit better. So it's kind of nice actually with these kind of these changes. Often they are a bit complicated, and you do need to think about it a lot. But you kind of need to go a step at a time. You need to do the easy parts and get to the hard part, and then, you know, when you're walking the dog and that kind of thing, let that idea ferment a little bit to figure out what the next kind of attack is. So anyway, let's just right now put our rig tab to 0, and let's see if there's any chance that this compiles now. Yes, and if we run that. Okay, so we're still getting the same thing that we saw before, which is that we get a trace, it generates a bunch of invalid guards where it's referring to a value that we had actually rolled back. So we still have a situation that the IR code we get is referencing values that we have already rolled back. So we know that because IR instruction 2 is referencing IR instruction 3. That's just not valid. These are backwards pointers. So we've trashed the IR quite thoroughly, and then it's not surprising that we get multiple traces then, because if a guard fails, then normally that means that this machine code can't be used, which normally means you need to generate new machine code. And if we have a guard that's got invalid operands, then we're kind of in undefined behavior territory, but it's not surprising that we get some extra things happening. So what we need to do next is have a little bit of a harder think about how to do that thing that we're trying to do. What we want is to emit two guards. One is that the table is the same one, that the runtime table is the same as the compile time table, and the other, the runtime key, is the same as the compile time key. And we need to have the invariant that these runtime values that we refer to are not computed using code that we roll back. So either we are referencing the wrong value here, or we've rolled back too much. It's one of those two. So we'll have to come back and have a look at that later, and maybe in the meantime have a bit of a ponder. It's going to be interesting. We'll take that a bit later. Done for now. Thank you very much for tuning in.